it's time for us to carry on. So where are we at? Well, we've talked about applications, and in particular, we've talked about volume. And most of the time when we do volume, it's usually a volume of revolution, but it doesn't have to be. And the basic idea is, let's take our volume and we'll break it into small little parts. In each part, we have a volume that's easy to understand. Now, today we're going to switch, and we're going to do a different geometrical topic, which is arc length. So our goal is to figure out, okay, imagine that we have a curve going between 2 points, and I want to know how much is the length of that curve. Now, there's a very easy way to solve, or at least I should say there's an easy case to solve, which is, suppose our curve is just a straight line. So I'm going from this initial point, x0, y0, and at this point, x1, y1, and I want to say, well, how long is that curve? Well, that's not so bad. What we do is we just use our distance formula, which comes from the Pythagorean theorem. So if you were to take this, you can say, well, the one side of our triangle is how much we change in the x direction, and the other side of our triangle, that's how much we change in the y direction, and this other side, that's our distance that we're after. So you use the Pythagorean theorem, and you can come to the conclusion that distance is the square root of x1 minus x naught squared plus y1 minus y naught squared. All right, life is good. But that's if what we're dealing with is a flat thing, a nice straight thing. What if what we're dealing with is not a flat, straight thing? So here's a curve. This curve is not flat, it's not straight. It moves up and down. And so the question is, okay, how long is it from this point to this point if I move along the curve? In essence, what we're doing is we have to say, imagine grabbing down to the ends and pulling it taut. What's that length? That's what we're after. Now, the basic idea of integration doesn't change. So our basic idea says, well, what's something we understand really well? And for us, we say, well, we understand straight line segments fantastically when it comes to length. So we say, all right, what we'll do is we'll break things up into small parts in such a way that our parts look like the thing we're really good at. So for us, what we'll do is we'll take our interval. So here we're thinking of going from A to B. And instead of thinking of it as one big long piece, we're going to break it up into little tiny pieces. So we're looking at each little piece, and we're saying, well, if we look at each little piece, it's not quite as moving up and down. So in the small, functions tend to look more or less very flat. And that's really where the power of calculus comes from, is when you look very close, things look much more like a flat thing, a straight thing in our case. We say, okay, well, what can we do? Well, for each segment, we say we can approximate the length by a straight line. Now, again, it's an approximation. It won't be exact. How do we get better? Not surprising. The answer is we subdivide into tinier segments. And if you look here, where we subdivide into even tinier segments, if you look at the straight line segment part versus the original curve, which is dotted, it's very, very close. So in other words, these sequences of straight line segments are doing a fantastic job of approximating the curve. And therefore, the sum total of these straight line segments, if we added them all together, would give us a very good and very reasonable approximation to what we're after. So that's what we want to do. So, what's going to happen? Well, basically we're going to focus on just sort of one piece. So think of it as there's somehow the ith step, the I plus first step, and we just want to say what's happening right there. So I just want to focus on this one piece right here. Well, what do we have? We get the following. That one piece, we have the change in the x values. So that's the xi plus 1 minus xi. And so in terms of this picture, that's this part right here. All right, that's the change in the x. Then you have the fxi plus 1 minus fxi. And what that is that's the change over here. That's your change in your y. So the xi plus 1 minus xi, the fxi plus 1 minus fxi. And we're after the straight line segment, so we apply our distance formula. We get the square root of xi plus 1 squared minus xi squared plus fxi plus 1 minus fxi squared. Now we do a little bit of algebra. Nothing too fancy, which is to say, let's divide out by this term. Or another way to say it is, let's pull this out of the square root. And so we do. We can pull this out of the square root. So that becomes delta xi on the outside. Once we pull it out, we're left with a 1 here. Now in this term, how can we pull it out? And the answer is, well, we really can't. So we got to compensate. The way we compensate is we divide by that xi plus 1 minus xi. And now the great aha is to sort of say, what does this look like? I have a small change in f over a small change in x. So looking at a small change of the output over that small change of the input. And this is the key, that this is approximately the derivative. You say, okay, therefore we have that the length of our line segment is, well, that says equals. This really should be approximately equals square root of 1 plus f prime of xi squared delta xi. All right, so now we have the length of one piece. And again, it's an approximation, so we don't have to have it be exact, but the key is it's an approximation that gets better the smaller that we get. And we're not surprised to see a square root, because square roots are built off of the Pythagorean theorem, and our notion of distance comes from the Pythagorean theorem. And so oftentimes whenever you see a distance involved, you should anticipate a square root. The good news is that now we have things like trig substitution. We can handle those square roots. They don't have to be so scary anymore. We can take care of them. So let's finish it up. Remember, this is just one piece. So to get the total length, we add them all together. And now, as you take the limit, the summation becomes the integral. And then the square root becomes a square root. Okay, well, that's not so surprising. 1 plus f prime of x squared. And the delta xi becomes our dx. All right, so there's our formula. Now you'll notice there's a box. That means that's important. You should memorize that formula. That's an important formula. Now, this is if we integrate with respect to x, we can have a curve x equals g of y. And if we do that, well, same philosophy. Just replace x's by y's. There's nothing sacred about symbols. We can change them as we need. All right, so that's more or less the theory for today. The rest of today is practice. So, lots of time for practice. One word of warning, and we say this many, many times, but no matter how often we say it, people don't believe us. When you're dealing with square roots are not as nice as you want them to be. So in particular, if you have a square root of 1 plus f prime of xi squared, you're like, oh, I'll know what to do. I'll just take the square root of 1, and the square root of f prime of x squared would be f prime of x. That makes it easy. Why do these mathematicians make it sound hard? Well, because we have to make it sound hard to keep our jobs, but also because it is hard. In essence, the problem is that addition does not work very well with multiplication. They don't get along very well. And when you're taking exponents, essentially that's a form of multiplication. So be careful. This means that we've got to pay attention. How do we handle square roots? Well, the answer is we're very careful with our notation, and we look for certain things. One of the most common things to do is look for a perfect square. We'll probably see examples where the inside is a perfect square. And when that's the case, we'll take advantage of that. If the inside's not a perfect square, sometimes we can make good substitutions. Other times we don't need to make a substitution. We can just integrate it as is. So we will see examples of all of those different things happening today. So let's start with our first example. Find the length of the curve y equals 2/3 x to the 3/2, where x goes between 3 and 8. All right. So we're in the right setting. This 2/3 x to 3/2, this is our f of x. So we say, all right, good news, we have a formula. So we have our formula length. We'll just write it down so we get in the habit of writing down the formula. A to b, square root of 1 plus f prime of x squared dx. All right. Well, what is a and b? 3 and 8. Because we know we're going between 3 and 8. 3 to 8. Square root of 1 plus. Now, let's take our derivative. What's the derivative of 2/3 x to the 3/2? X to the 1/2. Because the 3/2 comes down, you bring the exponent down, 2/3 times 3/2 is 1. And when you bring the exponent down, you subtract 1 from the exponent. If you subtract 1 from 3/2, you get 1/2. So this will become x to the 1/2 squared. Well, let's simplify that. What's another way to write x to the 1/2 squared? X. All right. Now, square root of 1 plus x. Do we need trig substitution for this? No. Okay. What do we do then? By the way, another way we could write this is x plus 1 to the 1/2. Can we integrate that? Is this something we know how to integrate? Yes, okay, good. Someone thinks we can. Essentially, it's just like u to the 1/2. The x plus 1 doesn't really do, the plus 1 is just a shift. It doesn't really change anything. It just shifts the answer. Well, all right. So this will become x plus 1 to what power? 3/2. And then in front, I multiply by 2/3. Evaluate from 3 to 8. So 2/3 will have x plus 1, which is 9, to the power 3/2. And then we're going to subtract 3 plus 1, which is 4, to the power 3/2. Now, you could do complicated things like say, well, 9 cubed is 729, and then take the square root of 729, which is 27. Well, that sounds complicated, so let's not do that. Do it the other way. Square root of 9 is 3. 3 cubed is 27. So, okay, so that's 2/3, 27. All right, do the similar thing here. The square root of 4, 2. 2 cubed, 8. 27 minus 8, 19 times 2/3 leaves us with 38/3. Now, geometrically, what have we just shown? What we've shown is that if you were to sketch this curve, x to the 3/2 power, from 3 to 8, I don't know exactly what it looks like, but let's say it looks like this. What that says that if you were to think of this as a piece of string and you grab the two ends and you were to lift it and then pull it taut, the length, that's 38/3. That's what we found. We found the length if you were to take this curve and make it a string pulled taut. All right. Let's try another one. Find the length of x equals 1/12 y cubed plus 1 over y for y going from 1 to 4. All right. Well, I guess one of the things we should point out is we should learn to recognize when to use certain tools. I think that as we move towards the next exam, that's probably going to be the hardest part. You're going to learn so many formulas over the course of the next several weeks. and then all of a sudden all these formulas become all jumbled up. So one of the things you want to make sure is, how do you know when to use which formula? So looking at this problem, when we see problems like this, what are some key words we should be looking for what we've learned about today? Yeah. So going forward, when you see words like length, you should be like, I'm going to use my length. Another word you might see is the word distance. Length and distance. So those are our key words for today. Now, there's a couple of things different. Sort of what's the big difference here? Well, I would say it's a more complicated function, but also notice it's x as a function of y. Now, one thing you could try to do is solve for y as a function of x, but most of the time, that's usually pretty hard, and it definitely looks hard here. So what do? Well, we say, look, there was nothing special about x. One of the things we said is we could still apply a similar formula if we had things in terms of y. So remember, we said, look, if we have x as some function of y, we can still do a similar thing. So it's the same process, same formula. We just change our mindset about what's our variable. So our length equals integral. I oftentimes use c and d when it's y. It doesn't matter. Again, c and d are just symbols. They're just placeholders. The square root of 1 plus g prime of y, quantity squared, dy, where this is our function g of y. All right, let's do a quick computation. What is g prime of y? One-fourth y squared. And the derivative of 1 over y? Negative 1 over y squared. Because 1 over y can be thought of as y to the power negative 1. So that's how we can think of 1 over is something to the negative 1 power. The negative 1 comes down, subtract 1 from the exponent. Now it's to the negative 2 power. So negative 1 over y squared. So we have that for us, c and d are 1 and 4, 1 to 4. Square root of 1 plus 1/4 y squared minus 1 over y squared squared dy. Well, we've now plugged in our formula. What's the next thing we need to do? Someone suggested to integrate. Well, probably we're a few steps away from that. U sub? Trig sub? Foil. Okay, good. Good. Foil. In other words, algebra. Algebra. Yeah? It's algebra. It's your good friend. You've been hanging out with algebra now for like 6, 7, maybe 8 years. And so you should definitely rely on algebra. See here, we've got a square. So if you see a square, it's like, okay, let me expand. Oftentimes, one of the things you need to do is work on rewriting the inside. It's a big technique. It's like rewrite what's on the inside. So let's see if we can do this. So we expand. 1/4 y squared squared. What would that give us? 1/16 y to the 4th. Minus 1 over y squared squared. What will that give us? So if I square this last term, it'll be 1 over y to the 4th, right? All right. Am I missing anything? I think I'm missing something, right? What am I missing? I've done the F and the L, so far I've done the full and foil. I'm missing the OI, right? The O and the I. Yes. So, In other words, what's the middle? What goes here? Because this is something that people often forget. So don't forget the middle part. Minus a half. Right? Because if you were to expand a plus b quantity squared, it's a squared 2ab b squared. So the 2ab, that's the middle term. That's what you get when you multiply these terms together and double. And very conveniently, almost as if it was planned, the y squareds are canceling. Wow, what are the odds? Probably pretty good. Now, can we do anything else to simplify? The 1 and the 1/2 can combine together. That's convenient. All right. 1 to 4 square root of 1/16 y to the 4 plus a half plus 1 over y to the 4 dy. Now, we've simplified algebra. Maybe we can push a little bit more. When you're dealing with the square root, what's the thing you hope for? It's like, in my heart of hearts, I really want this to be true. That it factors, not only that it factors as what? You want a square. Boy, if what's inside that square root is a square, life is good. You know, you've lived a good, clean algebra life. So, is it the case here that what's inside factors as a perfect square? And let me point out something very interesting. If we look at this, we know that came from a square, and we compare that came from a square. How similar are they? Yes, exactly. Oh, they're very similar. What's the difference? Yeah, one has a minus, one has a plus. Well, that suggests that somehow, since this came from a perfect square, this should also come from a very similar perfect square, but what should be our difference? So this part came from this being squared, so where should this come from? Well, I'll go ahead and say it. 1/4 y squared plus 1 over y squared squared. And you can check it, it does expand out that way. This is something that happens fairly frequently. Not that it would happen in random functions, but we don't ask for random functions anymore. See, when we do Calc 1, we're always like, okay, give me a function, any function. You never hear that in Calc 2. We're always like, here's this very carefully chosen function, because most functions don't work out too nicely. Well, square root square means that we get 1/4 y squared plus 1 over y squared. Now let's integrate. What's the integral of 1/4 y squared? One twelfth y cubed. You add 1 to the exponent, make it a cube, divide by 3. 1 over y squared, what will that integrate to? Minus 1 over y. Because you can think of 1 over y squared as y to the negative 2 power. Add 1 to the negative 2 makes it y to the negative 1, but then you have to divide by negative 1, which is where the subtraction comes from. And it's a definite integral, so we evaluate from 1 to 4. All right, we're almost there. We might as well finish it up. 1/12. 4 cubed, do you remember what that is? 64. Then we have minus 1/4. Then we're going to do subtract 1/12 minus 1. Well, what's a common denominator? 12. All right, so we can think of this as something over 12. 64 over 12. 1 over 4 becomes what? 3 over 12, so minus 3. 1 over 12 will become 1 over 12. Don't forget the minus, so minus 1. And 1 will become 12 over 12. Now be careful with your sign. This minus combines with that minus, so it'll become a plus 12. So we have 64 minus 3 minus 1, which should get us to 60. And then we're going to add 12, which gets us up to 72. So this would be 72 twelfths. Yes? No? 72 over 12, what is that also known as? 6. All right. Beautiful answer. Beautiful answer. All right. So that's an example where the inside becomes a square. All right. Find the length of y equals the square root of 1 minus x squared for 0 less than or equal to x less than or equal to a. All right. This should be fun. This should be fun. Well, let's try it. So, length. So we know we're in our length formula. We're going to integrate, and I'll go ahead and just put our bounds in 0 to a. The square root of 1 plus something squared dx. So let's look at this function. This is 1 minus x squared to the 1/2 power. If we take the derivative of this function, what do we get? Well, 1/2 comes down, 1 minus x squared to the minus 1/2, and then multiply by the derivative of the inside, which is minus 2x. So we end up with minus x over the square root of 1 minus x squared. If we clean it up, that's what the derivative is. The 2 and the 1/2 cancel. Life is good. So that's our derivative. That will go into our square piece right there. So minus x over the square root of 1 minus x squared. Well, so that's the square root of 1 plus x squared over 1 minus x squared. Now, what can we do here? We have our integral. What do we do? What do we do? Well, put on your algebra hats. If you saw 1 plus x squared over 1 minus x squared, what would you want it to do? Common denominator, put them together. What's another way to think of 1 in terms of 1 minus x squared? It's 1 minus x squared over 1 minus x squared plus x squared over 1 minus x squared. When we add those together, what happens? The x squareds will cancel off in the numerator. And so in the numerator you have 1. And the square root of 1 is also known as 1. And downstairs you have the square root of 1 minus x squared. All right, so there's our function we have to integrate. Now, you might just be one of those people who like to randomly memorize, like, oh, I recognize this as a function. Some of you might recognize this. But I tend not to memorize these things. What can we do to integrate this? Trig sub. What trig sub do we need to make? This is a sine one. A squared minus u squared. So if you let x equal sine theta, what will dx equal? Cosine theta. The square root of 1 minus x squared, what would that equal? It would be 1 minus sine squared, which is cosine squared, which would become cosine. So this would be equal to the integral. The top we'd have dx. Oh, I'm sorry, I forgot to write my d theta there, which is cosine theta d theta. On the bottom, square root of 1 minus x squared, which is cosine theta. So that's good news for us, because the cosines are going to cancel. Woohoo! What else we need to do, though? Get our bounds. All right. So suppose we know that x equals 0. So we put in x equals 0. For what angle of sine do we get 0 out? 0. So this becomes 0. Now, suppose x equals a. For what value of theta do we get that a equals sine of theta? Okay, so the question is, a equals sine of theta. What does that tell us about theta? Yeah, it's the inverse function of sine, so arc sine of a. So that's what theta is. So that's our upper bound, arc sine of a. Let me write that a little bit more cleanly. So this is 0 up to arc sine of a of d theta. Well, what's the integral of d theta? It's theta. And we're going to evaluate from 0 up to arc sine of a. And if we evaluate that, what do we end up with? Arc sine of a. And that's our answer. Okay, good. Good. It's clean. Nice, clean answer. By the way, does anybody recognize this curve? It's a circle, the square root of 1 minus x squared. And what's happening? Well, if you think about the picture about what's happening, you have this curve here, and you're going from 0 up to a. So what you're trying to find is you're trying to find this length here. Now, you might say, well, where does arc sine of a fit into this picture? And the answer is, it turns out that this angle here is arc sine of a. And so the length is the same as the angle on the inside. That's a nice fun fact about circles. Okay. Let's try some more, because we have lots of these. Maybe we can start speeding up. Okay. So, find the length of the curve y equals 1/2 the square root of x times x plus 2 times x plus 1 minus 2 natural log of square root of x plus square root of x plus 2 from x equals 1 to x equals 5. Okay. Now, there's a hint on this one. Let me show you the hint. Hint. It has a nice derivative. dy dx is x times x plus 2. Okay, good. All right, so that's going to save us a lot of work. Okay, so the length. Well, integral a to b square root of 1 plus, and instead of f prime, I can write dy dx squared dx. That's another way to write the formula, because we can think of the f prime as being the derivative. Well, so for us, where do we go from? What are our bounds? 1 to 5. We have the square root of 1 plus, and we plug in the square root of x times x plus 2 squared. Well, let's work on this. What happens? Yeah, so we're taking the square root of something, then we're squaring it, and they will cancel each other. So we get 1 plus x times x plus 2. Now what can we do? Okay, so we can multiply out, expand it. It's a very common thing when you're trying to simplify. All right, so we just have to figure out what to do with this 1 plus x squared plus 2x. Now, it might help when you're working with polynomials is to put them in the order of the power. It's sometimes written as x squared plus 2x plus 1. What can we do with that? What is it? It's x plus 1 squared. Yes! What? Wow! Beautiful! And this looked like it was going to be a terrible problem. This is turning into a lovely problem. It's it's calculus taking us for a walk on the beach. It's just a nice problem here. X plus 1 dx. All right. So, now we see this was a great one to work with. Easy to handle the square root. What's the integral of x plus 1? Okay, it's 1/2 x squared and x. Evaluate from 1 to 5. You plug in the 5, you get 1/2 times 25 plus 5. Subtract 1/2 plus 1. Well, if you take 25 halves and you subtract 1/2, how many halves are you left with? 24 halves, also known as 12. Add 5 to that, you get up to 17. And then don't forget, you also have to subtract the 1, giving us 16. A nice answer. Okay. Find the length of the curve y equals 1/2 x squared between 0 less than or equal to x less than or equal to 2. And then for no reason at all, just casually mentions that the integral of secant cubed is this expression. I'm sure that's just a copy and paste error. I don't know why they would put that in there. Okay. Well, let's begin. So, 1/2 x squared, this is nice. It's just a parabola. How hard could that be? And other famous last words. All right. So, our length will be integral. What are the bounds? 0 to 2. And then it's going to be the square root of 1 plus. Let's work through the derivative. We can do this in our heads now. Derivative of 1/2 x squared will be x. And then we need to square it. So we have the square root of 1 plus x squared. All right. How do we handle such a thing? Well, it's not to complete the square because there's no sort of x term. Someone said tangent. What does that mean when you say tangent? It's trig sub. Ah, nice. Good thing we learned that technique. It's coming in very handy here. All right. So what is our substitution? It's x equals tangent. What does dx become? Secant squared. The square root of 1 plus x squared. Oops, I forgot my d theta. Square root of 1 plus x squared. What does that become? Becomes secant. All right. So, trying to think about what we want to do about the bounds. Let's do it without the bounds for a second. Square root of 1 plus x. We'll put the bounds back in at the end. All right, so if we do this, this will become the integral. We're going to get a secant from the square root of 1 plus x squared. Then we get a secant squared from the dx, which combines together to give us secant cubed. Oh, well, that explains why they gave us some information about secant cubed. So let's see what that becomes. Well, I think this should be 1/2 secant theta tangent theta plus 1/2 natural log of secant theta plus tangent theta plus c. Now, how do I know that? Well, I'm copying. Now, if you didn't have it, do you remember how you integrate secant cubed? You integrate by parts, and then do a substitution, and then you get integral of secant cubed equals stuff, plus an integral of secant cubed, or minus an integral of secant cubed, and then you have to rearrange It's one of those fun integration by parts where you like do it once and you rearrange. Ah, the good times. Good times. All right, now we're not quite done because we've got to replace all these pieces. Secant, what will secant become? Well, square root of 1 plus x squared. What will tangent become? It'll become x. So it'll be 1/2 square root of 1 plus x squared times x plus 1/2 natural log of square root of 1 plus x squared plus x. Okay, so that's the integral. So now we're ready to pick back up. So this is going to be equal to that expression, 1/2, I'll put the x first, x square root of 1 plus x squared plus 1/2 natural log square root of 1 plus x squared plus x. And then we're going to evaluate this from 0 up to 2. Now when we plug in 0, let's hope something nice happens. The first term is going to go away because of the x. Because you plug 0 in there, that's 0. Inside the log, you're going to get a square root of 1 plus 0. Square root of 1 becomes 1. Natural log of 1 becomes 0. So that goes away. So what do we have? Well, we have 1/2 times 2, which is 1. Square root of 1 plus 2 squared becomes square root of 5. So I'm plugging 2 into the first term. 1/2 in the x become 1/2 times 2, and then square root of 5. Plus 1/2 natural log of, and square root of 1 plus 2 squared is still square root of 5, and then plus 2. And that's the answer. Now you kind of see, like, wow, these are not trivial, because 1/2 x squared is not a crazy curve. This is a parabola. And if it's this messy for a parabola, now you understand, like, we're really careful, because things can get really bad. All right. We have time to do one or two more. Set up an integral to find the length of y equals sine of x for 0 less than or equal to x less than or equal to pi. All right. Well, that's good. When you see the word set up, that should make you happy. We oftentimes put words like set up on exams. It means you actually don't have to integrate. It's all about getting the setup correct. And so now we focus on the setup. All right. So we have our length is integral a to b square root of 1 plus y prime squared dx. Because I can think of another way to write the derivative as y prime. All right. So for us, what's our setup? Well, our bounds are 0 to pi, given to us here, 0 to pi, square root of 1 plus derivative of sine, cosine. Cosine squared x dx. Now, what do we do next? Yeah, we're done. We set it up. That's the setup. Now you might say, well, wait a second. I want to know. No, you don't. You really don't. Because you can't know. This is one of the integrals you can't do. No matter how good you are, you can't do it. Now you might say, but what if I really, really want to know? Well, then the answer is you go and you do numerical integration. You can definitely get this to arbitrary precision. So if you want, you can go use your favorite computational tool and plug it in and get it to however many decimals it's willing to do. But there's lots of integrals that you cannot do. But we can set them up. And setting them up, that's actually worth a lot. Because look, you know, sure, computers can do the computations better than you. I mean, I don't want to sell you short. I think you're pretty good. But computers can't do the setup yet. That's your current advantage. So make sure you make the most of that and keep your competitive edge. All right, one last example. Find the length of y equals 1/2 e to the x plus e to the negative x between 0 and log 2. Out of curiosity, does anybody remember seeing this function before? This is called cosh. Hyperbolic cosine. Okay, does that help ring any bells? Okay, so imagine that you wanted to make a movie about something where he said, look, I got to go destroy something famous. And he said, okay, what's the most famous thing I can destroy? Well, they always destroy one thing in almost every disaster movie. Right? The Golden Gate Bridge. Right? Now you're probably thinking, wait a second, Steve, it's the Golden Gate Bridge. It's not the Koch Gate Bridge. Here's the thing. This shape, that's Koch. So if you hang a wire, that's Koch that you see hanging there. So every time you've gone to admire the Golden Gate Bridge and say, wow, that's a beautiful parabola. No, you were wrong. That's a beautiful Koch curve. All right. So, good. Now you know. Now you know. So, what do we have? Well, it's integral 0 to log of 2, the square root of 1 plus. All right, I'm just going to go through this quickly. Do you remember what the derivative of cosh is? Derivative of cosh is sinh. Right? You know, cosh is hyperbolic cosine. The derivative of hyperbolic cosine is hyperbolic sine. On a fun side note, do you know what the derivative of sinh is? It's cosh. It's cosh. It's even better than sine and cosine. You don't have that pesky negative coming in. Life is good. Life is beautiful. Now, at this point, you're probably thinking, great, but this does not seem to be very helpful. Here's a fun fact. If you take cosh squared and you subtract sinh squared, what do you get? 1. So 1 plus sinh squared, what does that equal? It equals cosh squared. So this becomes, oh, there's a log 2. 0 to log 2 of cosh. All right. Well, do we know what the integral of cosh is? It's sinh. And we're going from 0 to log 2, which means we have sinh of log of 2 minus sinh of 0. Now, you're probably thinking, all right, what is sinh? Sinh of x is 1/2 e to the x minus e to the minus x. Now, if you plug in sinh of 0, what do you get? You get 0. Sinh of log 2. Well, sinh of log 2 would be 1/2 e to the log 2 minus e to the minus log 2. E to the log of 2 is also known as 2. E to the minus log 2. Do you know that one? It's 1/2. So the minus you can think of as being 1 over. So it's like 1 over e to the log 2. 2 minus 1/2 is 3/2 times 1/2 gives us 3/4. So that's our answer, 3/4. And that's it for today. See you next time. Have a good day.